Materials. The materials you will need to perform this lab are reactants, solution A and solution B, 3 pipettes, 5 large test tubes and a test tube rack, 2 graduated cylinders for accurate measurements, 5 beakers, a stopwatch, and most importantly, safety goggles, because safety is our number one priority.
Procedure. Fill a beaker with distilled water to be used later to dilute solution A.
Use a pipette to measure solution A in a graduated cylinder. Start by measuring 9 milliliters and pour that into the first test tube. Use N-1 to represent how much of solution A should be put into the test tube 2. N is 9 milliliters of test tube 1. Therefore, test tube 2 will have 9 minus 1, which is 8 milliliters. Test tube 3 will have 8 minus 1, which is 7 milliliters of solution A. Follow the same procedure of measuring solution A and continue until all test tubes have the appropriate amount of solution A.
Use a pipette to measure water to dilute solution A. Start by measuring 1 milliliters and pour that into test tube 1. Use the expression N plus 1 to represent how much water should be put into test tube 2. N is 1 milliliters in test tube 1. Therefore, test tube 2 will have 1 plus 1, which equals 2 milliliters. Test tube 3 will have 2 plus 1, which equals 3 milliliters of water. Continue steps until all test tubes have the appropriate amount of water.
The test tubes should now contain 10 milliliters of combined volume at different concentrations of diluted solution A.
Measure 10 milliliters of solution B and divide it between 5 beakers. Make the test tubes accessible to all members comfortably so that solution B can be poured in at the same time to obtain accurate results.
Have the reacting species on standby and give a verbal count so that solution B can be poured at the same time. Have one member recording the time each reaction occurs. This individual should also be responsible for recording data during the procedure.
Watch the reaction go to completion and use the recorded and written observations to make calculations on the relationship between concentration and the rate of reaction.
To calculate the final concentration of solution A, we will use the C1V1 equals C2V2 formula. Using the data from experiment 1, initial concentration of solution A is 0.1 moles per liter, initial volume of solution A is 0.009 liters, and the final volume of the dilution is 0.01 liters. Let's rearrange the formula and sub in our known values to solve for the final concentration of solution A. This is what the equation will look like. Therefore, the final concentration of solution A is 0.09 moles per liter. To calculate the rate of reaction of this concentration of solution A, we will use the formula rate of reaction equals change in concentration over change in time. The values recorded during the experiment are initial concentration equals 0.09 moles per liter, final concentration equals 0 moles per liter, the initial time is 0 seconds, and the final 28 seconds. Plugging these values into the equation, we can solve for the rate. Calculating these numbers, we get negative 0.003 moles over liters times second. The rate is negative because it is the rate of disappearance or consumption of solution A.
Sources of error. One source of error in the experiment was an inconsistency in time for reaction port, which resulted in one of our trials displaying inaccurate results. This in turn caused an inaccuracy in the reaction time for certain solutions, as a color change was observed for test tube 2 and 4 before the others, even though they consisted of lower concentration than test tube 1, meaning they should have had a longer reaction time in comparison to 1.